want to solve some 3x3 systems with you. And just as with 2x2 systems, there are multiple ways to solve the system. I'm going to be using the elimination method with these problems today. So let's jump in with this particular problem. Our goal is to find the ordered triple that would be a solution to all three of these equations. They each have an infinite number of solutions, but they only share in this system one ordered triple that would make them all true. So here we go. We're going to use the elimination method, and here's what it requires: that we grab two equations and eliminate a variable. You can choose to eliminate x's, y's, or z's, but grab two equations to do it. So when I'm looking at this, I see the x and the negative x in the first and third equations, so I'm going to grab those two. So I'm going to rewrite equation 1 and equation 3 right here. So I have x minus 2y plus 2z equals 11. And I have negative x plus 3y plus z equals negative 8. And when I add those two together, the x's will be eliminated. And we have y plus 3z equals 3. Now I'm going to leave this equation alone for a minute and come back to the original system. And here's what I need to do next. I need to grab a different pair of equations and eliminate the same variable. So I haven't used equation 2, so it definitely needs to be in the next pair that I use. So I can use either equation 1 and 2 or 2 and 3 and make sure I eliminate x again. Mathematically, it doesn't matter which of those pairs you use. Since I see that the 2 and the negative 1, the coefficients of x, are already opposites in these two, I'm going to grab those two, but it really is almost arbitrary. I could easily have grabbed these two. So let me jot down that I'm going to use equations 2 and 3. But notice, because I'm going to eliminate x, I'm going to need to multiply equation 3 by 2, because I need those coefficients to be exact opposites. So equation 2 is unchanged. It is 2x minus y minus 3z equals negative 1. And equation 3 is now negative 2x plus 6y plus 2z equals negative 16. And when I add these two together, I have 5y minus z equals negative 17. Now here's how this is helpful. I now have two equations with two unknowns, and I can put those together. Let me do that right here. So I have y plus 3z equals 3, and 5y minus z equals negative 17. So I started with a 3x3 system, and now I have a 2x2 system that you can't quite see. Let me bring that down just a little bit. A 2x2 system that we know how to solve. You can actually use the elimination method or substitution method to solve this system, and you'll find the y and z coordinates of the solution to this system. But for now, I'm not even going to pay attention to this. I'm just focused on solving this system right here. I'm going to continue using the elimination method. So you can multiply the first equation by negative 5 and eliminate the y's, or multiply the second equation by 3 and eliminate the z's. I think that's what I'll do. So my system becomes y plus 3z equals 3, and 15y minus 3z equals negative 51. So when I add those, I get 16y equals negative 48, or y equals negative 3. And I'm unable to write in a horizontal line. Let's continue. And let's see if I can write horizontally now. We're going to substitute -3 into one of these two equations. I'm going to just choose to put it into that first equation. So I have -3 plus 3z equals 3. Solve that equation. So I get z equals 2. So I have the z coordinate and the y coordinate of the ordered triple that is the solution to this system. I'm now coming back to this system and grab any of the three equations, substitute in my y value and my z value to find my x value. Since the coefficient of x is 1 right here, I'm going to choose this equation, but again, you could choose any of the three. So I have x minus 2 times y plus 2 times z equals 11. So let's do some arithmetic here. We have a +6 and a +4. So we have x plus 10 equals 11, or x equals 1. So now we know the coordinates of our solution. The ordered triple that is the solution to this system is 1, -3, 2. And you could substitute this ordered triple into all three equations. And if it works in all three, you have confidence that you've done it correctly. If it fails in any of them, we know we have a mistake somewhere, because it should be a solution to all three. Let's do another one. Let's solve this one. So again, we're looking at the system to determine which variable we should eliminate. And it really is your choice. Mathematically, it doesn't matter. So I'm looking for two equations in which I could eliminate a variable easily. And in this problem, I see that y seems to be a nice choice. Right here in equations 1 and 2, if I add those together, the y's will be eliminated. So that's what I'm going to do. I'm going to use equations 1 and 2. They're already opposites, so I don't need to multiply by any number. Just jot them down. And then add, and one of our variables will be eliminated. So we have 5x minus 3z equals 23. Now I leave this alone for a minute and I come back to my system and I grab a different pair and eliminate the same variable. So now I need to bring in equation 3 into this problem. So I'm going to use equation 3 with 1 or equation 3 with 2. And I think I'll use equation 3 with 1. They already have opposite coefficients. So I'm going to use equation 1 with equation 3. But I'm going to need to multiply equation 1 by 3 so that they'll be exact opposites. So let's do that. So we have 6x plus 3y minus 6z equals 39. And x minus 3y plus 3z equals -8. And when we add those together, we get 7x minus 3z equals 31. Now we can put these two equations together in a 2x2 system. Let's come up here and do it. So we have 5x minus 3z equals 23, and 7x minus 3z equals 31. And now we're solving this system. I'm going to multiply by -1 and add. It is possible to just subtract those equations. If you're comfortable doing that, that's totally valid. But I'm going to multiply by -1 and add. So we have -5x plus 3z equals -23. And 7x minus 3z equals 31. And when we add those equations, we have 2x equals 8, or x equals 4. So we have our x coordinate of our ordered triple. Let's keep going and find the z coordinate. Substitute 4 into either equation you choose. I'm going to choose that first one. Doesn't matter though. So 5 times 4 minus 3z equals 23. And we solve this equation. So we get z equals -1. So now we have the x coordinate and z coordinate of our solution. So we are just a y away from the solution for this system. Grab any of those 3 equations. I like this first equation because I'm solving for y and the coefficient of y is 1. But again, you can choose any equation you like. So I have 2 times 4 plus y minus 2 times -1 equals 13. And we finish solving this. What do we have? 8 plus 2. Let's just make that a 10. So we have y equals 3. So take care when you present your ordered triple, because we might not have found them in the x, y, z order. I found the x first, but then y is down here, and then z. So the solution to this particular system is 4, 3, -1. Let's do one more. We're going to solve this system. You'll notice it's missing a couple of terms, but that's all right. And in fact, it will make it shorter to solve this particular problem. For this system, you can choose to eliminate x's, y's, or z's. I'm going to choose to eliminate z's in these first 2 equations. Notice in doing that, I'm going to need to multiply the first equation by 2. So our equation becomes 8y minus 2z equals -42. And I'm going to add that to the second equation, which I'm not going to change. And it looks like that. When I add these together, I get 5x plus 7y equals -23. Now, normally I would have to go back and grab a different pair to eliminate a variable. But notice equation 3 is already missing the z. So we can use that to our benefit. We can use that equation as is in combination with the equation we have just found. So we have 3x plus 2y equals -5, and 5x plus 7y equals -23. And we need to solve this 2 by 2 system. Remember, you can choose to eliminate x's or y's. The decision is yours when you're doing the problem. I'm going to just choose to eliminate the y's. I'm going to need to make sure I multiply one of them by a negative number because they are the same sign and I want them to be opposite signs. So I'm going to multiply this one by -7 and this one by +2. And when I do that, I get this. -21x minus 14y equals 35. And 10x plus 14y equals -46. When I add those together, what do I get? I get -11x equals -11. So x equals +1, and we have our x coordinate of the solution. Let's pop 1 back in here. And now we can solve this equation. So we have 2y equals -8. So y equals -4. And last we need z. So I come back to this system here. And I can grab either of these 2 equations to solve for z. I think I'll use this first one. So we have 4 times y minus z equals -21. So we continue to solve. And we end up with z equals 5. So our solution to this system is 1, -4, 5. And I hope now you'll go practice solving some 3 by 3 systems.